Okay, so we'll now find another use of our expressions for the half-axis, the major and the minor half-axis A and B. Namely, they can be used to express the orbital period of time in terms of these quantities. In other words, we can express the period of time it takes for a particle to complete one orbit in terms of these two half-axes. If you recall in the beginning of when we first started to consider these central forces, we showed that the area swept during a finite time interval would be the same. It would be constant. Or expressed alternatively, we can say that the areal velocity is constant. Like this. So the area dA swept over time dt is constant at all points in the trajectory. Let's now integrate this expression over a complete period. Which should simply give the area, since we have dA dt integrated over time for a complete period. The magnitude of the integral should be L over 2m multiplied with large T. Now it's known that the area of an ellipse is given by pi AB. And this gives us a way of expressing the period it takes for the particle to complete one orbit in terms of the half-axis A and B, as announced. In the previous lecture, we derived these expressions for the half-axis, both depending on energy, whereas B is depending on L, and A depends on K. So if we insert these expressions into the period, I get this, and I do this by expressing B in terms of A. So from the definitions of B and A, we see that B over L can be expressed in terms of A. So if I now insert this, or substitute that into this equation, I'm able to express the period solely in terms of A. And this is the main result, namely that the square of the period is proportional to the cube of A. And this is Kepler's third law. This can be used to approximate planetary motion, for instance, where you have an elliptical orbit, in order to relate the period of the orbit to the magnitude of the half-axis. What we've done so far is to find an equation for r as a function of theta. So we basically express how does the radius in the orbit change with the angle. But in principle, it should also be possible to obtain an expression for r or theta as a function of time. So whereas expressing the orbit in terms of r as a function of theta gives us a qualitative idea of what the orbit looks like, or a quantitative, in fact. We get exactly an expression for how the orbit looks like. The time development describes more precisely how the particle moves, its velocity. So in a situation where we're more interested in that, we would have to go back to this expression, which, as you may recall, originates from the conservation of energy and conservation of angular momentum. We've just integrated over time here, and correspondingly integrated over the radius here. So let's see if we can solve this. For our particular case of an ellipse, in which case we know that the energy is negative, so I replaced E with minus absolute value V. And I can extract this constant outside of the integral to be left with this. So note that so far I'm considering now an undetermined integral. I haven't specified these limits yet. So when solving this, we have to keep in mind that we have t equals the general solution for this integral plus some undetermined constant. Now, if we consider this expression inside the root, we may see some familiar quantities. For instance, k over the absolute value of E is equal to the major half-axis, or half of it, A. Whereas this term is related to B. It follows from our definitions over there. This is B squared, actually. So the integral takes this form, which is starting to look manageable. So how to solve this? Well, one idea could be to make, to complete the square here in order to make a substitution. So I take this expression and I add 0. I add a squared minus a squared, plus a squared minus a squared, which allows me to write this. So I combine these three terms into this term here, and the rest is expressed by the eccentricity defined over there. So it means that we can write this term under the root sign like this. So we have r dr divided on the root of this. And now we can see that it might be advantageous to define a new integration variable, namely r minus a, because that would just give a constant contribution over here, and then just a single variable under the root sign. So let me show you what I mean. This is supposed to be a xi. It's a Greek letter xi. So if I substitute r minus a as follows over there, I obtain this. Which may be considerably simplified, because this root here is just A epsilon sine xi, which cancels this term. And this integral is trivial. It's supposed to be integrated over xi. So the first term here is just a constant, and this term becomes sine xi. So we've then obtained that the time in the problem can be parametrized by this xi in the following way, and I've absorbed A into this prefactor plus some constant, which depends on the initial conditions. Now, let's choose the initial conditions so that the constant again is 0. And then we'll consider what this means physically. This is the same as we did when we expressed r as a function of theta. So we then have time equal to this, and r is expressed over here in terms of this psi. So by choosing the initial conditions in such a way that this constant is 0, we now see that psi equals 0 corresponds to 0 time, so sort of the original time for our system. Whereas the position vector for psi equals to 0 is the perihel. So the way to sort of understand or interpret this parametric representation of R and T is that they're both parameterized by this parameter psi. And as you increase psi from 0 and above, R develops in this way and time develops in this way. Possibly, if it was possible, we could have expressed psi, isolated psi, and expressed it as time, as a function of time, and then reinstated it here to find R explicitly as a function of time. In this case, I think it would be kind of messy. So this is a more convenient way to represent the time evolution of the trajectory. So to summarize what we've done, we've considered the Kepler potential and found a compact way of expressing the particle trajectory, the orbit, both in terms of r as a function of the angle, but also in terms of this time evolution of the parameters. So having done so, we'll now move on to a new topic. And the topic is scattering in a central force field. So let me now define what kind of situation we're considering here. Assume that we have some uniform current or stream of particles which are incident towards a scattering potential. These particles can be electrons, planets, alpha particles, whatever. Anything that can be modeled by, in a context-appropriate way by these point masses. It's incident So we have some kind of situation like this. We have a bunch of particles, or depending on the context, some kind of object incident towards some kind of scattering potential or some force center, V of r. This V of r could be a heavy star, for instance, in the context of planets or asteroids. And in the context of electrons, you could have an electron beam incident towards some kind of electric potential caused, for instance, by heavy nuclei. So it really depends on the context, which means that this is a quite general situation. And assume that the potential is such that as you approach infinity, or as you escape from this scattering potential, this force field, the force resulting from this potential goes to zero. So at an infinite distance, the particles feel no potential energy. But we haven't said anything about whether the particles are, whether the potential is attractive or repulsive. All that we're saying is that the force should go to 0 as the radius approaches infinity. So it's still quite general. We may characterize the incoming particle flux by its intensity I. And intensity is defined as follows. It's the number of particles that pass through a cross-sectional unit area per unit time. So it's the flux through some unit area per unit time. Since we haven't specified whether the potential is attractive or repulsive, we can, in general, envision two different scenarios for how the particles will move when subjected to this potential energy. So basically, we have said that the force acting on the particles at r equals infinity, so in some circle here, should be 0. So the particles are incident here, experience no force, and hence should just be moving rectilinearly. They're incident here, in a linear way. And then, as they approach this force center and start to feel its effect, they will either be bent towards, if it's an attractive potential, they will be bent towards it, and then escape linearly here, since there's no potential energy anymore, or they should be repelled, if it's a repulsive potential. So they enter here, and are repelled. These are basically the two situations we have. So the trajectories start off rectilinearly, deviate from this as they approach a pass, as they pass the force center, and then become rectilinear again as the force recedes, as the particles escape. And we're now going to define a very important quantity which gives us a way to quantify precisely this scattering of the particles. It's a quantitative measure of how the trajectories of the particles deviate, how they are bent by this potential energy. The differential scattering cross-section is defined as follows. It's the number of particles scattered into a specific orbital angle, d omega, per unit time, divided on the intensity of the incoming particles. So this this orbital angle is defined as follows. So basically what this differential scattering cross-section says something about is if we have incident particles here, how many are scattered into a specific angle per unit time, per intensity. And to give you an idea why this is such an important quantity, consider the fact that depending on what the potential energy is here, what we have here, which is a scatterer, these trajectories will take different shapes. So we can actually obtain information about what is scattering these particles by considering how they are deflected, how the trajectories are changed. So for instance, you have incoming electrons and you have some nuclei here. Depending on what kind of substance you have here, which scatters the electrons, the trajectories take different shapes, which can be measured experimentally, and thus can be used to infer information about what we have here. And this is just one example. And the dimension of this differential scattering cross-section is, as you might have suspected from the name, area, or square meters. And you can see this from the fact that you have the number of particles, which is dimensionless, it's just a number, scattered into this orbital angle, which is also dimensionless, per unit time, so it's second inverse, divided on intensity. And intensity is defined as the number of particles through a unit cross-sectional area, so inverse area, per unit time. So you have inverse area, inverse time, these two cancel, and you're left with area. As I've mentioned previously, when analyzing a problem in classical mechanics, we should always be on the lookout for symmetries in the problem. And since you have central forces, we know that we have this rotational symmetry. Which essentially means that since this potential depends only on the radius of the energy, if you define this line here, a particle incident here will experience exactly the same potential as a particle incident here if this distance is the same. So we have this circular symmetry around the axis of incidence. So it means that we can just integrate the phi dependence and obtain 2 pi. So that the only thing which matters is at which angle they approach the potential. Okay, I promised you that we should have a reference group meeting, so could the reference group please step up?